Next presentation, this is from the wet chemical equipment supplier RENA. Damian Brunner is going to talk about wet chemical innovations in silicon heterojunction and TOPCon cell processing. Damian is a senior R&D manager at Solar and Battery wing of RENA Technologies. Damian, the floor is yours.
Thank you, Shravan, for the nice introduction. I hope you can hear me well.
Yes.
Okay, I try to share my screen. I hope you can see it.
Yeah.
Okay, very nice. Okay, let me get the pointer. Okay, now I'm ready. Yes, thank you very much for the opportunity to be here, for having me and sharing our latest results. And also special thanks for the whole TaiyangNews team for organizing and providing this beautiful platform so we can come together here online and share our latest developments. In our talk, I'd like to focus on some new innovations from the wet chemical topic, for especially focused on heterojunction, and also prepared some slides for TOPCon solar cells. Here a brief outline of our presentation. First, we like to go into the details of texturing and cleaning for heterojunction solar cells. The second topic will also focus on copper plating. Here we will present two solutions for high throughput inline plating of copper for heterojunction. And in the last part, as already mentioned, a brief outlook on opportunities for processing, wet chemical processing for TOPCon solar cells. Yes, let's start with the texturing and cleaning for heterojunction solar cells. Here you can see our main product for texturing and cleaning. Our product name is the BatchTex N in a silicon heterojunction version. It's a batch tool for 400 wafers which we processed in one bath. At the bottom, maybe most interesting and important, you can see our schematic sequence. So after loading, there is an optional organic clean, which can be either based on ozone-based cleaning if you have rather high quality incoming material, or optional hydrogen peroxide SC2, pseudo SC2 clean we would recommend here. Followed by SDR cleaning. This is alkaline-based and also strongly depending on the quality of the incoming wafer. Then we would have an ozone-based pre-condition and cleaning to have a very high homogeneity, low distribution of the pyramids, and to adapt the height of the pyramids, to be able to adapt the height pyramids very well to the following processes of and depending strongly on the quality of your preservation afterwards. Of course, after texturing, then the rinsing becomes more and more important. This is not depicted here in the beginning. It also plays a major role, but then the combination of cleaning and rinsing is a very, very crucial point. And here we would like to only focus on the cleaning. The first step is the post-cleaning step, ozone-based to get rid of the organic material. Also ozone-based etchback and HF-based metal clean in the last part. This all has a throughput of about 7,500 wafers per hour up to G12, and also half-cut wafers can be processed. On the next slide, here you can see some field data where we've applied exactly this sequence in a production environment and compared it to alternative supplier solutions. And we obtained very nice efficiencies, even with a small efficiency gain of 0.1%, driven by a gain in fill factor and VOC. And this is a clear proof that our basic concept, which is efficient and cost efficient on electrical level and also very cost effective. In the past months, we also took a deeper look in a lab environment on our process and compared it to some competitors' sequences out there in the field. And we picked one major player here, and we looked into more details and we compared our sequences, and we come to the conclusion that our sequence is much more lean, and this is good for footprint and costs. But how about electrical performance? Here a small variation of this competitor sequence and compared it to our BKM. And on IVOC level, about 745 millivolts, we are exactly on the same level. And also, if we look on the efficiency, we on par. So we can offer here at least as good electrical performance and a strong advantage in footprint and consumptions. So let me move to the second topic here: inline plating solutions for heterojunction solar cells. Maybe copper plating. So of course we like to replace copper by silver due to the reasons all of you know very well. So let me very quickly give you an introduction of our approach. We use our inline technology, so the wafer is immersed only single-sided to the electrolyte. And we contact the wafer on the rear side, and the contacts are kept dry all the time. If we apply an external rectifier, a voltage or current, then the deposition takes place in the structured surface on the front side. Here you can see an actual picture how this is realized in the copper bath. And the major advantage of this approach, which is protected by IP, we can achieve very excellent homogeneities. Since we use the whole conductivity of the wafer, we don't need any carriers, any seed layers. And of course, there's no contact on the plated side, which is very beneficial for high homogeneities and high throughput. We assume that this technology is validated and ready to go for mass production, since this is based on years of experience in our inline technologies from edge isolation, and also we had spent some time already in R&D with copper plating. Next, I'd like to show you our two approaches, how we could help the industry for applying copper plating to silicon heterojunction solar cells. So the first approach, also recently suggested by this CSEM, Gatalahowicz presented this in Milano. The concept is that you print a very thin, very low laydown metal, silver metal seed layer, cover it by a low temperature silicon nitride, the whole area, and due to the power structure of the finger, you can straight away apply the copper plating, and the nitride protects any deposition between the fingers and any ghost plating, or however you want to call it. So here a picture of one of our first wafers. So this is working more or less straight away with our technology. And here we obtained very nice looking wafers, very good distributions, homogeneities, and the adhesion is also perfect. So this is from mechanical and tool perspective ready to go. And we estimate the potential for silver reduction at least to be in the ballpark of 50%. Coming to the second approach, as mentioned before by Peter Wolf, this is like masking the whole surface with a organic photoresist and structure it as well. And then we can go with this structured mask into our plating system. And after a little of optimization, we've been able to achieve very nice looking fingers with a nice aspect ratio close to 2. So we have a width of 12 micron and height of 17 micron. And of course, the big challenge for such fingers is the adhesion. And after a little optimization or an optimization rounds for the pre-treatment, we've been able to increase this significantly. So without any pre-treatment, you can just apply the plating and peel off the grease straight away. And we've managed to have a very good adhesion here and pass all tape tests. So next steps would be to, from the stability aspect, to move on to module testing. And yeah, this is ongoing. But besides reliability and adhesion, the electrical performance is also very important. So we compared, after some optimizations of the process, we are on par for the plated cells with our screen printed reference we obtained from industrial partners. And of course, there's a potential for further efficiency improvement, but this is an early stage. We are on the same level, and there are no any issues due to plating, and a big potential. Of course, this is strongly depending on the level and quality of the incoming wafer, the efficiency level, and yeah, this is the results you can see here are first on hybrid solar cells. So only the front side is plated and the rear side is still printed. And one of our future tasks is then move to double-side plated solar cells. So next, I like to go to a quick overview for options for processing, wet chemical processing in TOPCon solar cells. So here you can see a generalized process flow for TOPCon solar cells. In blue marked are the wet chemical processes. On the left-hand side, we focused on inline processing for edge isolation and poly wraparound removal. Our product here for edge isolation is the inoxide blue, so hot alkaline inline etching of the rear side, and also hot alkaline inline etching of the poly wraparound removal. And our product name is in polyside. On the right-hand side, there are alternative solutions, so-called cluster solutions for edge isolation and poly wraparound removal. And today I like to focus on the cluster solutions. Before going into details, a very brief introduction for those of you who might not be familiar with this term. So you load your wafer for PERC. Short look back. There's an optional inline densification in a thermal anneal. So you grow a thicker glass, thickened and intensify the glass layer on the front side. Then for TOPCon and PERC wafers, you would go into a single side HF step and remove the glass layer on the edges and on the rear side. Then the front side glass is acting as a mask. And then you can move to a batch system and smoothen the rear side or edge isolate the junction, or remove the poly wraparound on the front side. And in the last part, you clean your surfaces or even remove the glass if appropriate. RENA can provide the PERC cluster and TOPCon junction isolation cluster. Is already available, and the poly wraparound cluster will be coming soon. I will show you some data in a moment on our R&D status. So just very quick for the single side HF process, this is our product. This is a very simple schematic, and we can offer throughputs of close to 7,000 wafers per hour on a very small footprint here. For the following batch process, this would be one example for our process flow for the Bowen cluster, for the actual smoothing and cleaning. So to guarantee a good homogeneity and process stability, we have a little pre-oxidation in ozone, the actual alkaline etching, and an ozone-based clean afterwards. So the whole process chain is completely hydrogen peroxide free. Here you can see some data we obtained in an early stage, but still very interesting. It's a TOPCon process, and here in blue marked are 3 different small variation of RENA processes, and as a reference in red we process the process flow, which is mainly distributed in China and applied to TOPCon, as far as we know. So the sequence is pseudo SC1 based, all the cleanings, and there's a huge dependency on hydrogen peroxide. And as mentioned, our solution is ozone based. So all processes work on the same efficiency level. We even see a small efficiency advantage for cleaning in the VOC. Here on the bottom, a very important parameter is for the junction quality isolation, the IRF2 value. All groups are performing on the very good values. And our two groups here, we took a detailed look into faster processing and optimized the HF process for the glass removal. And even with faster speeds, we actually can reach lower JREF2 values. So as mentioned, a small preview for the poly wraparound cluster. Here, as you can see, a strong variation of in our cluster performance. So this is still in an optimization phase, where we are still looking in different directions. But anyhow, we already have some very promising results. And as a reference, plasma etch poly wraparound removal is applied. So a nice combination. For example, this group here, the efficiency is already on the same level, and the JREF2 values are already very good. And also the thermographical images show no light up at the edges. In comparison, for this plasma etch treatment, which is not the best performing day here, to be fair, usually they perform better, but either way, in this batch, it come out like this with some light up in areas at the edges. So this is my last slide from results point of view. Here we put together all the best performing processes for TOPCon, so the best texture, the best Bowen edge isolation cluster, and the best poly cluster in one batch. Did also a little variation in the cleaning process. So cold would be again is referring to ozone-based processes, and we compared it to a standard texturing at Fraunhofer ISE. And with our new and latest adaptation of additives for TOPCon, we are able to reach very low reflectivities, which show nicely in a gain in JSC. And coming to the chase, in combination of this good adapted additive and an ozone-based optimized cleaning, we obtained efficiencies close to 23.8% in efficiency, and this is validated by some Fraunhofer colored ISE measurements. So this brings me to the conclusion. Just very briefly, we showed you results for cost-effective and proven high throughput solutions for texturing and cleaning of silicon heterojunction solar cells. We've presented two different options for copper plating in an inline system and ready for high throughput productions with masking and at least reduction of the silver consumption by low temperature silicon nitride. We showed some nice efficiencies for combining all the best we can offer on the cluster branch for TOPCon processing. And lastly, I have to mention, due to time reasons, we couldn't go into the details of the inline solutions for TOPCon. However, all processes, the inoxide blue and the in-poly side, are running in mass production, and maybe we can share the results in the next conference next year. So with this, I'd like to thank you for your attention, and especially thank all co-workers and colleagues at RENA R&D who contributed to this work and prepared a lot of slides. They actually did all the nice work, and yeah, they deserve all the credit. So thank you.
Okay, thank you, Damian. That's very nice presentation. But what really very interesting for me is RENA first time presenting something on heterojunction, a plating solution. So, you know, we had RENA in past in our conferences where more or less you were focusing on TOPCon. I would not say you were against, but you were never in favor of heterojunction, a plating solution. So I would like to ask you, what really changed this ideology?
It's quite simple. Three things. One is what made us hesitate is the big challenge of masking, the ITO. This is nothing in our hand, and we nothing we want to be dragged into to provide a solution. So people approached us providing already this masking system. This was one thing. The second one is now with this low temperature silicon nitride. So the masking task is already solved by the supplier. So this is one driving force, and the growing interest. This is the second one. And after little testing, we had fast, quite good results. So these are the three key things which make us change our mind, and now we are focusing even more on this topic.
Right. So I don't know if I missed it, but so what are your commercialization plans? So is it production ready, or it is already at a customer's place?
We are still in R&D phase. It's not, we are not yet with the silicon heterojunction solution at customer place. For TOPCon, yes, but for heterojunction, we are still open for partnerships.
Oh, okay. So then there is also a question from our audience. So I'll frame it in a different way. Like, now you have both solutions for TOPCon and heterojunction from plating side. So which one you think would be soon commercialized? Which has the prospects?
This was difficult to say. We are open to both options. Wherever the force and the belief and the pull is even stronger. A feeling from personal point of view, right now the pull is even a little bit stronger for the silicon heterojunction community. But yeah, the race is open. Yeah. So
yeah, sure.
Let's see.
and PV is always full of surprises, so we'll never.
Yeah, sure. Yeah.
Great. Okay. Thanks a lot. It was very nice to hear from you.
Yeah. Thank you very much.
And please answer the questions. There are some in the chat box.
Will do. Thank you very much.
Thank you.